Hello, my name is Matthew Psaradakis and I am a science enthusiast from Greece with a great interest in philosophy too. So, could you please introduce yourself to us?
My name is Sky Darmus. I'm half German, half Greek, and I do research in quantum gravity.
Very nice. Before we start, let's define the term scientific theory. A scientific theory is an explanation of an aspect of the natural world that can be repeatedly tested and verified in accordance with the scientific method using accepted protocols of observation, measurement, and evaluation of results. Where possible, theories are tested under controlled conditions in an experiment. In circumstances not amenable to experimental testing, theories are evaluated through principles of abductive reasoning. Established scientific theories have withstood rigorous scrutiny and embody scientific knowledge which is widely accepted as valid. Scientific theories are testable and make falsifiable predictions. They describe the causes of a particular natural phenomenon and are used to explain and predict aspects of the physical universe or specific areas of inquiry. So, let's begin the interview with the first question. Are you ready?
Yes.
What is a superposition according to space particle dualism theory?
So superposition, space particle dualism theory started off with interpreting what a superposition is using what I call the similar worlds theory, or similar worlds interpretation. So I believe that we, or our consciousness, coexists in all the worlds which are temporarily indistinguishable for us. For example, when you have a photon entering a beam splitter, we learn from quantum mechanics that it goes through the beam splitter and it is reflected at the same time in superposition. And my explanation is that while it is flying, while the photon is flying, there's no difference for us between it going through and being reflected. We don't see a difference because the photon is not measured yet. It hasn't hit a detector. When a detector is hit, maybe one detector on this side will have a blue light and the other detector will have a red light, and then we can tell the difference. And this is also a principle in philosophy, the equality of indiscernibles from Leibniz. He also said that things that cannot be distinguished are somehow true at the same time, and I think that applies to quantum mechanics. And so the number of the worlds we are in at the same time, those are classical worlds. Their number, the logarithm of their number is entropy, the entropy of the universe. Because entropy, the entropy is the number of microscopic states which cannot be distinguished, which are microscopically identical, same temperature, same appearance. So that gives us a good definition of entropy. Using quantum mechanics, we can say it's the number of the different quantum states that are indistinguishable. And so the main thing that this solves is entanglement. Because if the reason why there's entanglement, this is nothing mysterious. Entanglement is because in each of those worlds, which are indistinguishable, impulse, the momentum must be conserved. So if you have two particles that are generated together for momentum conservation, you need to have their spins to be orthogonal, like in right angle. So in each one of those worlds, they're always right angle. And in mainstream physics, it's kind of mysterious because you have one particle here being fuzzy and another part here being fuzzy, and there's no clear connection between them. And this entanglement is going with more than the speed of light, is instantaneous. And so in this similar worlds interpretation, it's not mysterious at all because they are orthogonal in each of the worlds. So a superposition in similar worlds interpretation is basically always a superposition of the whole universe. It's not single particles. and so it appears very natural and doesn't need any mini wormholes or something like that in order to pass the entanglement information. It's purely natural, nothing mysterious going on. But there's one thing that is a bit mysterious about it. It's this reliance on, you see, the wave function collapses at the same time everywhere. So when you measure this particle having a spin like this and the other particle having a spin like that, this this collapse of the wave function that it decides to have this spin, it goes to the other particle. It's simultaneous. The wave functions collapse simultaneous, and this is something which is difficult to grasp in Einstein's setting, where simultaneity is kind of not allowed because it's undefined. So we have an issue there, a conflict between Einstein's theory and quantum theory, because one says there is no simultaneity, and then the other theory kind of relies on it. So there must be a preferred frame of reference somehow. Might it be the microwave background, or we don't know, Milky Way, Earth? We don't know which is the preferred frame of reference. And I've thought about experiments that could be used to find it.
I think that Einstein said that quantum entanglement is like spooky action at a distance.
Yeah, so in this theory, it's not spooky. It's not spooky anymore. And this another way to explain the similar worlds interpretation, which is very visual, is in classical theory, in classical mechanics, you have something that's called the phase space. It's basically a space with infinite number of dimensions where each point represents the universe at one moment in time, and similar states of the universe are close to each other. So one point represents the universe at one moment in time. So you could imagine the passage of time like one dot of consciousness in phase space going through this phase space, and that's the passage of time. And you have 3 dimensions for a space and 3 dimensions for impulse. And so you have 6 dimensions for every particle. So, but the problem with this view is that, wait a moment, in quantum mechanics, you don't have definite positions for particles. They're fuzzy. So you cannot really use this phase space, or can you? Well, you can if you extend this point, this conscious point, which represents the universe at one time, you extend it into a cloud. So that cloud is like all the similar states of the universe, which we cannot distinguish. So every time you measure something, the cloud shrinks and then grows again and shrinks again and grows again. So that's how you can visualize quantum mechanics. But then you stumble upon another problem. This explanation seems nice, but it's kind of too simplistic, because if you use this interpretation, all you would get is a probability mountain for where you are. Like the position, the particle, or you, the most likely position is here, let's say. So that's the peak of the mountain. But we know that the probability of particles to be in a place are waves and not just simple mountains. It's not just a mountain, it's a wave. And that's where the second part of the theory comes into play, which is about quantizing space. So we know that from Einstein's theory, we know that space and time are dynamic, and that gravity slows time and makes rulers shorter. And if space is something that can bend and twist, then it should be something. It cannot be nothing. It must have some substance. It must be made of some constituents, some smallest constituents. And most people in quantum gravity research agree with that. They think that there must be some smallest constituents. And most people just simply take the Planck length as the size of the constituents. And I think that's a very simplistic approach, because if it's really the Planck length, then you can never measure it. You could never make any experiment to ever test such a theory, because it's just the Planck length just too small. So I thought about what could be those constituents. And I read a book about string theory. I'm not a fan of string theory at all, but I read about 5 books about it. That one was from Brian Greene. I think it was called Elegant Universe. And there was, I think, one comment where he said that there's a certain similarity between elementary particles and black holes, because they're so simple. Black holes, they just have mass, momentum, and charge, and nothing else. So I thought, could it be that maybe elementary particles are just black holes? And that's is a very simple idea. It was even mentioned in Big Bang Theory by Sheldon when he met with Hawking in the series. So, but the problem is, so the idea would be that maybe maybe space is made of bubbles that are overlapping. So when you want to go from A to B, you don't go straight, you go on the surface of bubbles. It's more easy if you draw just circles. You draw a paper full of circles, and then you draw a line which is going only on top of those circles. So that's a way to visualize that. And that's so where do these bubbles come from? So obviously there's the vacuum energy. I guess most people have heard of vacuum energy. The quantum vacuum is basically saying that virtual particles popping in and out of their existence, and the more energy they have, the shorter they exist. So how many are there, and how much vacuum energy is there? The simple approach, which everyone is taking, including me, is that you say there's one fluctuation every Planck length. So I'm not abolishing the Planck length, I'm still using it, sort of. And so you also have to quantize how many different fluctuations you can have. So I am quantizing the wavelength of the particles. So it's one Planck length for the wavelength again. So, but the problem is, if you have only one fluctuation every Planck length, and your bubbles are the size of a black hole, if you take, for example, an electron and say it's a black hole, it would be 10 to the power of minus 57 meters, and the Planck length is 10 to the power of minus 35 meters. So they would be too tiny, they could not really connect. So I thought, what if they're like black holes, but much, much bigger? So a black hole, it has a gravitational constant here, but I replaced the gravitational constant by a new constant, which is like gravity, but scaled up to the strength of electromagnetism. So you have something like a black hole, but one which doesn't represent gravity, but it represents electromagnetism. And then you have a resting electron would be 10 to the power of minus 21 meters. And that's kind of close to where experiments are. Experiments are down to 10 to the power of minus 18 meters. And it's sort of close. And if you go to high energies, so I'm basically saying, a black hole, its size is proportional to the energy inside it in standard theory. So in my theory, what I call elementary spaces, these bubbles that make up space, they are like these classical black holes, which depend on basically the mass energy in them. And so at 9 times 10 to the power of minus 17 meters, the bubble, the elementary space, the space atom, so to say, becomes bigger than its wavelength. And then we have a chance to make experiments to prove that it's that these things actually exist. So this is the first theory, which is using atoms of space which have a variable size, can be smaller or bigger. So then you have this huge ocean of these bubbles, and these are all two-dimensional spheres. So you would say, okay, does this mean our world is two-dimensional? In some way, it would be, but actually, I say it's here. This is the number of connections. So it would be actually 2.999999999 dimensional with 35 nines there. So it's almost three-dimensional. And so it's 35 nines there, and that's the reason why electromagnetism is 10 to the power of 36 times weaker than, stronger than gravity.
Why
Is
gravity?
incredibly stronger than gravity.
Why gravity is the weakest force according to your theory?
Yeah, because it's a side effect. So let me explain this a little bit better. So when a particle goes from A to B, it goes zigzag all the time, going from elementary space to elementary space. And when you have gravity, you have more of these bubbles here. The reason why you have more of these bubbles here is because when you have a charge, like let's say you have an electron, it emits a lot of virtual photons, and those virtual photons, also called gauge, they're gauge bosons. They are responsible for transmitting electromagnetism. So they also have the elementary spaces, and so you have more of these bubbles here. You always have the background bubbles, the granular space, as I call it. But then you add a charge here, and then you have even more of them. So, or you have a quark, like protons and neutrons, they're made of quarks. And so you have a lot of virtual gluons, and the same happens here with the gluons. So Earth is made of protons and neutrons, right? So it has a lot of these bubbles coming out everywhere. And so there's a higher density of these space atoms. And so there are more pathways leading through those areas of space, through those regions of space, I shall say. Areas would be a surface. So that's what gravity is. So we can still use Einstein's notion of a geodesic, a most straight line in curved space. That's what Einstein said. But I say no, a geodesic is not a most straight line in curved space. It's a most straight line in granular space. And that's a good explanation for why the universe is so flat as it looks. There's a flatness problem. This doesn't mean like flat like Earth, but it's a cosmology problem that says that's about why is there no spatial curvature? Like according to Einsteinian cosmology or Friedman cosmology, the universe could be highly curved. For example, it could be like the surface of a four-dimensional sphere. So when you look straight, if it's small enough, you could look yourself on the back. You could see yourself from the back, like some sort of reversed mirror. And so a triangle would have more than 360 degrees. And if it's an open universe, it would have less than 360 degrees. So, but we don't see all this. We see a perfectly flat universe. And in Einsteinian cosmology, you need to have a huge coincidence happening. That you need to have a very sensitive balance of the initial expansion rate and and gravity. They have to be in balance. It's like throwing a stone. It must be the perfect speed. And so actually the fine tuning is so extreme that it's like balancing a needle on its top for millions of years. So that's why people came up with inflation theory, which in my opinion is a very, it's a primitive way to solve the problem. You just say, oh, the chance for such a flat universe is 1 in 10 to the power of 60, 62 actually. So let's say that in fractions of the first second of the Big Bang, the universe expanded to a factor of 10 to the power of 60. Like 60, power of 60, 62. Okay, that's the only reason why they invent inflation. And Roger Penrose, who received the Nobel Prize last year, it's actually my childhood idol, Roger Penrose. He said that the chance for a universe to be flat due to inflation, it's even more unlikely than to be flat from the beginning. So it doesn't do any good. But there's no other explanation there. So, okay, Penrose himself thinks he has something, he has some theory. The good thing about him is that he has a lot of ideas. Yeah. So according to me, I agree, according to SPD, I agree with Newton, what Newton said about the universe. He actually said that the reason why the universe doesn't collapse is because it doesn't have a center and it doesn't have any edges. So where should it fall into? In which direction? You have infinite many stars pulling from this direction and from that direction and from up and down. So it just doesn't move. But in Einstein's theory, things are strange. Even gravity from opposite direction is still contributing to the overall curvature. But this is really not a neat, subtle thing, because when you take Einstein's field equations, they are only designed for calculating a single object, like a single Earth, a single black hole. Even if you have two black holes colliding, you cannot get an exact solution. But somehow they take Einstein's field, the equation for a collapsing black hole, turn it upside down, that it looks like an expanding universe, and they say, oh, it actually is an expanding universe. So when Einstein learned about the expanding universe, he said, oh, gosh, why didn't I predict it? Well, Friedman had some models about this, but it's really not a theory. You cannot say that Einstein's theory predicts the expansion of the universe and the Big Bang, because it doesn't predict the speed of the expansion of the universe. And my theory actually does. I made this t-shirt here. This is the speed of the expansion of the universe at, no, sorry, that's the back side. This is the front side. This is the speed of the expansion at every given moment. So h is the Hubble parameter, and h0 is the Hubble parameter at this moment in time. So this equation tells you how it changes over time. And because in my theory, I say the expansion of the universe is not influenced by gravity. So it doesn't slow down or things, complicated things like that. It's just expanding like it does now. It's an accelerated expansion. And why is it accelerated? Because according to my theory, the expansion of the universe is the universe is expanding because it's trying to level out the entropy increase in black holes. You know, black holes have this huge entropy, and the reason why they have this huge entropy is they you cannot tell what is inside. It could have been a star, which is most likely, but it could have been a huge pizza that collapsed and formed a black hole. It could be just anything. People say black holes have no hair. There's no hair theorem. sounds a bit sounds a bit nasty. And I don't quite agree fully with this theorem, because when you examine black holes closely, you see that actually when they collapse, when a star gets close to the critical circumference that turns it into a black hole, time dilation goes infinite. So time slows down infinitely. So it actually never really becomes a black hole. But the radical relativism would dictate that we are just living in a space-time, and so you could just go around the corner in space-time. So although for the outside observer, you never fall into the black hole, but for you who is falling into the black hole, everything is normal and you fall into the black hole. I think we cannot maintain this radical form of relativism, because we need a passage of time, because quantum mechanics is a dynamical theory. It's not like Einstein's theory, which is purely deterministic. The future is not yet there yet in quantum theory. We don't know what happens in the future, and even the past is not fully determined yet. It's measured, and wave functions are collapsing. So, but back to the topic of entropy increase. So if you feed a black hole linearly, like one donut per second, or one donut per minute, let's say, then the mass increases linearly, but the entropy is increasing exponentially. And why is that? It's because the entropy depends on the surface area of the black hole. That's Bekenstein's formula for the black hole. It's the surface area. And a lot of people think that means that the universe is holographic and all sorts of things. I don't think so. think it's over-interpreting the equations. But anyway, if the expansion of the universe is leveling out this entropy increase in black holes, then it must also go up like this exponentially. So that's why the universe gets faster and faster. And so for 300 years or more, about 300 years, we always thought that the universe must have started with a low entropy. This is a notion that was before cosmology, and is coming from thermodynamics. Things get messier. An egg falls to the floor, and it cannot jump back on the table again. Only if all the molecules kick each other in exactly the right way to reassemble the scrambled egg and push it back onto the table. So that's why people thought the initial entropy must have been low. And Penrose, for example, he assumes the initial entropy of the universe was low. And he says because there were no black holes. It could be a huge mass with black holes which have high entropy. But then he actually admits that that we actually don't know. Maybe there were a lot of black holes, so-called primordial black holes. Hawking was speculating about them. And actually, we have to assume that there must have been primordial black holes, because these, you know what is at the center of every galaxy? There are these huge supermassive black holes. And everyone knows they can never, ever have formed from stars. It's just not possible. So it must be something, people say maybe dark matter. I just saw an article yesterday. Well, in SPD, in space particlism, there's actually no dark matter and no dark energy. You don't really need them. It's because when you take the equation that I just showed on my T-shirt, and you so other paper. One moment. You can derive the age of the universe. So this looks a bit complicated, sorry. So this is the speed of light, and Z is the redshift. So redshift is because when the photons fly through space, redshift can be because of, for example, a car is moving away, so the light will be redshift, will be dragged out, stretched out because of the speed. So it can either be the speed or it can be the expansion of space itself.
Doppler effect.
Yeah, the Doppler effect. So, but for the universe, we assume that the other galaxies are not really moving away. It's space itself expanding.
Mm-hmm.
So this equation gives you the distance to any galaxy in the universe, according to my theory. And it's pretty simple. So how do things look like in Einstein's theory? I don't think we have to say it's part of Einstein's theory. Let's say it's the cosmology of Einstein's theory, which is more based on Friedman. He derived those equations. He used Einstein's field equations to talk about cosmology. So there, it's a bit different. You don't have the three, and you have different equations for different distances. So when you go to redshift 0.2, you need another equation and then another equation. You derive them from some differential equations. And so it's very complicated. So the difference between my model and the mainstream model, it should be quite obvious in observations, right? So, and actually I think it is quite obvious. So which one is right? We give, me and the mainstream, they give different distances for those remote galaxies. My equation gives, for the close galaxies, those are not in the local group, but outside of the local group, because inside the local group, there's not much expansion of space. So for the nearby galaxies in other groups, I give 3 times higher distances, larger distances. And for the most far away galaxy we know, I think it's called GZ11 something. The redshift is 11. I say it's 39 times further away than we think. And so when I put in the redshift here for the cosmic microwave background, do you know the cosmic microwave background is very cold. It's 2.7 Kelvin, very cold. So how hot was it initially? It's called the decoupling temperature, is when light is not coupled anymore with all the electrons and photons and atoms around, or nuclei, and it can travel freely. So that's when the universe becomes transparent. In most books you hear it's 3000 Kelvin. I needed a more accurate figure, and that's 2900 Kelvin. So when you divide today's temperature and the initial temperature, then you can get the redshift of the microwave background. Because the reason why it's so cold is because it's stretched out. The universe has expanded, and that's what cooled the cosmic microwave background. In the mainstream, it's called the radiation of the Big Bang, the leftover radiation, the leftover heat from the Big Bang. And when you plug in that Z value, then you get the age of the universe. I don't know if you know that movie. There's a movie where you have a giant computer which is calculating the answer to all the questions in life and the universe.
42.
And it takes millions of years to calculate, and the answer is 42. Yeah. And it took many months after I calculated the age of the universe, I realized that it's the same number as in that movie, 42 trillion years. It's just a coincidence, but it's a nice coincidence. Yeah. So that seems, to many people, it seems crazy. How could we be so wrong about the age of the universe? The first thing to remember is, in all the scientific magazines now, a very popular topic is the so-called trouble with Hubble. They look at the supernova data, and they get one age of the universe. It used to be 13.6 billion years, and then they look at the CMB and they get another age of the universe, 12 billion. So now you have any value you can imagine from 12 to 14, and the measurements are so accurate that all the scientists say it doesn't make sense that it is measurement inaccuracy, because our confidence level is this here and this here, and there's just no overlap, and this is a hint for new physics. And many astronomers actually told me that they always found this age to be much too short. Imagine it's just slightly above the age of a sun-like star. Our sun is about 5 billion years now, and it has a total life expectancy of 10 billion years. And our universe is supposed to be 13.6 billion years or something like that. Is not very reasonable, because Earth has so much iron, so many heavy elements. I forgot how much iron it is exactly, but it is a huge amount of iron, a large percentage. And the sun, for example, doesn't produce any iron at all. For producing iron, you need a star that's 8 sun masses, and not even then it might not produce iron. It needs to be 8 sun masses and reach a certain temperature, which is bound to many conditions. So it's very difficult to get so much iron. You need to have many hundreds of suns exploding in order to get this much iron, in my opinion. So I also calculated a chemical age of the universe. But the most neat way to check if if my age of the universe is correct is to look at the distances of stars. So how can we know how far away those stars are? Well, we can look at the type LA supernova. They have a very standardized brightness, so they're always about this. They're called standard candles, and so we can look at how the luminosity of supernovae is decreasing with the square of the distance. You know, gravity decreases with the square of the distance, and the brightness also decreases with the square of the distance. So a good way of testing our distances is to check if they decrease with the square of the distance. So in cosmology, we don't directly use luminosity. We use something else called magnitude, and magnitude is an inverse logarithmic measure. So it starts with minus 20 and something, and so the lower the lower the magnitude is, the brighter is the thing. So the star. So so I would like to share with you wait a moment, here, share the screen. Okay, do you see it?
Yes.
Okay, so these are the SPD distances to magnitude. These are all the galaxies. Here you see the distance in light years. And those dots are the different magnitudes. The higher the magnitude, the less bright it is. So it's a bit very counterintuitive, this measure, this magnitude thing, but it's convenient for calculations. So so here we can take an average. We can take an average brightness star, and in thought, we push it away and increase the distance, and that's how the magnitude would change. Now we can overlap the two graphs and see how well it fits. So it should the luminosity should decrease with the square of the distance, which means that the magnitude increases with the square of the distance, and that's what you see here. The red dotted line and the yellow line, they're aligned with each other. So what happens with GR, with Einstein's theory? We see it here. We see the distances are very different. We see that the red line, the dotted line, and the yellow line, they don't align with each other. Not very well. And it almost looks like it's going straight. The next here is SPD. We zoom in here. Now it's 10 to the power of 10 light years. And we see a perfect alignment again for SPD when we zoom in here. And let's look at GR. Again, it doesn't align very well. The yellow line and the red dotted line, they don't align. Then let's zoom in again. And even closer, again, perfect alignment. For GR, not aligned again. It's a very discrepancy. And then only when you zoom in, you make the last zoom in. Here it aligns. And then it also aligns for GR. The reason is there is no cut. I only have one equation, and they have different equations for different distances. Yes. So yeah. So this is one way of showing that there's an issue, and some people have realized that. Quite a lot of people. There are Korean physicists. They have noticed that there's a problem with the luminosity of far away supernovae. And they said, oh, maybe the laws of physics change over time. I think this is just another ad hoc explanation. It's like a bit similar to inflation theory. You just invent something in order to save a theory that has a problem, instead of deeply thinking about the principles involved. This is the one way of testing SPD. The other way of testing is calculating the age of stars. In Einstein's time, even Einstein doubted a little bit the age of the universe that falls from his theory. He didn't quite believe it, to be frank. Because there were many rumors about, or people were talking about stars that are older than the universe. I personally don't think that's a very straightforward proof to show that the universe is older, because those estimates for the age of stars, they sort of depend on how much heavy elements are inside the star, And so that already depends on sort of a timeline for the universe. So it's very circular reasoning. It doesn't work quite well. And I say the perfect indicator for the age of the universe, except from this luminosity thing, is the age of dead stars. Because for a star to die, it needs a long time. And the smaller the star is, the older, the longer it takes. So for the sun, it has 10 billion years life expectancy. And the very giant stars, they have a very short life, like 10,000 only. So, but when you get to smaller stars, we know then they have trillions of years. So if you have a star that's like 0.2 sun masses, it takes trillions of years for it to die. But yet we find white dwarfs that have 0.2 masses only. So you could kind of fiddle around and say, oh, maybe there's some mass shedding. But the problem is when you get to under 2.25 sun masses or 2.3, it's like there's no mass shedding at all. It just keeps its mass because there's no very powerful explosion. So I calculated how old are all those white dwarfs we see around us. I think we shouldn't be seeing a single white dwarf or almost no white dwarfs. So when a star dies, becomes a white dwarf, it has a temperature of about 100,000 Kelvin. Like it's pretty standardized. It's like that temperature. And then when you see a white dwarf having a certain temperature, they cool down pretty quickly. You can know how long it took. They're very super simple thermodynamic equations to calculate how long it takes for it to cool down. You just need to know how bright it is and how much it shines out, and you know how much it cools. And so I calculated those. Let me go to page 322. A moment. And 22, and I will share the screen in a moment.
Mm-hmm.
Here we go. Share screen. So here on the very right side, you see the age of the white dwarfs. You see a 10 to the power of 11, 10 to the power of 10. So they have all huge ages. So it's the time for the cooling. I separately cooling age. I calculate how long it takes to cool, and I also calculate. I didn't write it down, the calculation. I also calculate how long it takes for it to die. So I add the two together, and you have quite a few which are 10 to the power of 13. And so the question is, let's get out of the shared screen. So how many are within, you see me again? Yeah.
Mm-hmm.
So the question is, how many of those are within the edge of the universe I calculate, and how many are within the edge of the universe that the mainstream has? So I looked at 35,000 white dwarfs. It's pretty much all the white dwarfs that exist. And if you use Excel, you can calculate the age all simultaneously. Basically, in order to not make it too complicated for the computer, you just every step in the calculation, every multiplication, every division, you just put in a different row. So 32,000 of them were older than the age of the universe in the mainstream, because there's so many that are so tiny and so cold. It just shouldn't be. And there are so many cosmologists and astronomers who have complained about it and say it just doesn't make sense. And so you have now a lot of physicists and I know many physicists who are maybe they're particle physicists, and they say, no, I don't like cosmology. It's just such a mess. I don't like it. So they know there's a problem. They really know it. and so you don't have so much enthusiasm about cosmology these days, and I hope to change it with my theory.
Mm-hmm.
And so 99.3% of those were exactly inside the age of the universe I calculated, the 42 trillion years. There were only 214 or 250, I'm not sure, which stepped out of the line. And I think maybe they have some slight inaccuracy in their mass or brightness, because I calculate these all using a mass estimate, and this could be slightly off. So it's to be expected you have some few which step out of the line.
Mm-hmm. Shall we continue to the next?
Yeah, you have some questions still?
What happened before the Big Bang according to your theory?
According to that's a bit of the crazy part.
Yeah.
So I say that that I adhere to this Copenhagen view. The observer collapsed the wave function, also called Wigner von Neumann interpretation. So I say that there's no physical world if there are no observers. So if you detonate all atomic bombs on Earth, and nobody's in outer space right now, then the universe would have to have no wave function anymore, because the wave function is basically the knowledge of the observer. So basically it would have to fall back into a state which has observers. And I devoted a whole chapter on how it can get from the last observer to sort of the first observer, and using morphic resonance. So yeah, so that's basically what happened before the Big Bang is, or the Big Bang is, the last observer died. That's what happened. So, but actually, I don't really have a true Big Bang. I think we need a definition for Big Bang, because even in the mainstream, you never know which is a Big Bang. Is it so hot or so hot? When do you call it Big Bang? Is a process, right? So, but I think a good definition for a Big Bang is to have this nucleosynthesis temperature, which is also a requirement for stars, because primordial nucleosynthesis, Big Bang nucleosynthesis, is the only real prediction that Big Bang theory makes, like other than the universe expanding, but it's not really Big Bang theory, it's just an observation, and Hubble made it, and that's the Hubble parameter. So according to my theory, you can actually derive what was the the initial temperature of the universe by looking at all those black holes, because if the universe expands in order to compensate for the entropy increase in black holes, then you can find out how much you can squeeze it down until you cannot longer make it smaller. That's when your black holes just disappear. You make them smaller, the universe is smaller, becomes smaller. And when they just disappear, then you arrived at the maximal density. And I used my own distances. They're mainstream evaluations for what is the entropy density of the universe, but I cannot use them because my distances are larger, so I have a lower entropy density than the mainstream. So I calculated the initial temperature of the universe, and it's only 6,000 Kelvin. You can have no, even the sun is hotter. You can have no primordial nucleosynthesis, but that's no problem, because if the universe is very old, then you will have both light elements and heavy elements both. And it's actually not known by many, but Big Bang theory has a huge issue with the abundance of the light elements. There's the lithium problem. Very few people have probably heard of the lithium problem. There's four times or five times discrepancy with the lithium abundance. So Yeah, so I say there was no real Big Bang, and I also don't think that there was a matter-antimatter war, because in no experiment on Earth have we ever seen that new matter can emerge out of a matter-antimatter annihilation process. You have photons, you have electron-positron pairs, they all annihilate each other, and cosmologists go out there and say, okay, we have so many photons to so many baryons, and we say, oh, we think initially it was the same number, and we say, okay, maybe it's like one uh, 1 million protons, 1 million positrons had 1,000,001 electrons, so one was left. And you would think, oh, this is some sophisticated calculation, but they just thought, okay, maybe baryons and photons were the same number, and then they got set off in this way. But this is pure speculation, and we never got any experiment that suggests it. So I don't think that the universe became out of pure light. I also think that this whole way how Big Bang theory is portrayed is it comes from theology actually. Actually, it was a priest, some bishop, who invented Big Bang theory like roughly the same time.
Georges Lemaitre, I think.
Yeah, right. Yeah, thanks. Yeah, and yeah. So in my theory, I deny the Big Bang, but I don't deny the expansion. And so I say the beginning of the universe was pretty boring. I thought about calling it the Big Boringness, because absolutely nothing. I invented like 5, 6 different names for it, or the big slowness, or retardness, slow, right? So because it was very, very slow, my T-shirt, on the back of the T-shirt, I calculate the initial speed of the expansion, and it basically depends on how small the first primordial black holes were. So I deny dark matter, because I say that if the universe is so old, and if 90% of the gas has been used up already, the mainstream admits that 90% of the gas in the Milky Way has been used up. How can 90% of the gas being used up just after the lifetime of one star like the sun? So to me, it's obvious that 90% of it has been turned into stars that are already not shining anymore. They're burned out stars. And that's why 90% of the Milky Way is basically dark. And nobody would feel that it's strange or that it's mysterious dark matter, because if you don't have any prejudice as to the age of the universe, you wouldn't think it's strange that you don't see a lot of stuff there. I mean, if the universe is let's say it's very old, for some time people thought the universe is infinitely old. Even to the 50s, Fred Hoyle, he thought he was very popular, and he had this eternal universe theory where the universe expands, yes, but matter is created in between. So that was still acceptable in the 50s. So from that, it should be obvious that there are no observations that show you very clearly, oh, the universe must be very, very young. And the reason why it's so young in the mainstream is because the universe, when it expands, it has to fight gravity. So in standard theory, the Big Bang, it must be very violent and very fast in order to not collapse back. So it starts with 17 times faster than now, 17 times the present speed, then slows down and then accelerates again, like it does now, like after 8 billion years. That's the standard theory. And you can imagine if it starts at 17 times the speed it has now, you end up with a very short age of the universe, because if it was so quick, it must be very young. But if you believe in a continuous expansion, exponential expansion, entropic expansion, I call it, that's also the name of my recent paper, was 50 pages and contract to 30 pages. Then the universe becomes very old, because it was started very slow, and it's like a snail going very slow. That's why it's so old. That's why you arrive at a very old age. But yeah, so this is about the cosmological aspects. I didn't tell you anything too much about gravity. I told you the concept of how gravity works, but not the consequences for observation. And I also didn't tell you about my experiments in Greece, in near Sparta, Scala.
Mhm.
If my theory is basically saying that there are no gravitons. Gravity doesn't come from mass or energy, but it comes from the number of quarks. Now, according to my explanation, you should think that anything that has charge has gravity. Also, electrons. The problem with electrons is that they're emitting virtual photons, but for a virtual particle to reach very far, it has to have very little energy, because the higher the energy is, the smaller is the time it can exist. Because virtual particles are popping out of existence, right? So you have very small energy, and when you get to 40 meters, the energy is already so small that the elementary space of it is smaller than the Planck length, and that's when my theory says that it doesn't contribute to gravity anymore. So I say there's electromagnetic gravity, and there's nuclear gravity, like strong force gravity. I also call it subgravity and hypergravity. Hypergravity is from hypercharge, because quarks, they have this color charge. 3 colors add up to 0. Like for normal charge, you have plus and minus adding up to 0. And here you have 3 colors, and they're not really colors. They're just called colors because they have this property of having 3 elements adding up to 0. So they just call them colors. So the strong force is intermediate. Mediated. Sorry, it's mediated by gluon from sticking. So it's a very strong force. It's gluing together. It's holding the atom together, the protons, and they have a special property of being self-interacting. So a gluon will emit another gluon and will interact basically with themselves. So that's why you can reach infinity and your elementary space will still be big, because it's not just one virtual particle and then it dies, but one gives rise to the other, and so you can, this hypergravity, it reaches infinity. It can get everywhere. So the electromagnetic gravity, I call it subgravity, it can be ignored in all normal circumstances. It's still important to do experiments to find it, and I imagine some, but it's not the dominating gravity. Dominating gravity is hypergravity, and it depends only on the number of quarks. So so quarks, they have hypercharge. Hypercharge is usually denoted with a Y, with a big letter Y. So obviously, if you have an atom, you have a proton, has 3 colors, it's neutral. So Y is 0. But what is not 0 is the number of quarks. So black, the sets and set theory, it's blackboard bold. It's written like this symbol here. It's like this, like double lines, blackboard bold. So the set of all the quarks inside an object, the absolute value of it is just a way for me to say the number of quarks. So this is a symbol I invented to mean number of quarks. So so one might think, number of quarks and mass, isn't it the same? I mean, I have more protons, I have more mass, I also have more quarks. Isn't it the same? Well, it's not the same at all. It's kind of similar, but not the same, because if you have iron, like this is the Newton's formula for gravity, like square of the distance, but with quarks, number of quarks here, and a different constant, which is not used together with mass, but with number of quarks. So if you look at iron, and I did experiments with iron in Greece, and water, you find a big difference because iron is huge atoms. They have like 56 protons and neutrons, and they have a they have a lot of negative binding energy. And when you check its atomic mass and the number of protons and neutrons, you see there's a discrepancy. It's not the same. So from that you can see that there's a big difference. So I say that the gravitational constant that everyone is using, we measure it with iron balls usually. We have a long stick, and we have two iron objects, and then we look how the stick is going back and forth. It's pulled by the gravity of the iron objects, and then the torsion of the string pulls it back again. So by looking at the angle of the swinging and the time, you can measure the gravitational constant, and that's what Cavendish did 300 years ago. By the way, he didn't have a degree because he was a very shy man. He couldn't face the professors when they make the exam. Couldn't even talk to a woman. So, but he measured gravity very accurately. He had a small hut, and he would go there and with magnifying, I don't know what is it called, to look far through glasses, and he would, in order to not disturb the experiment. So I did the experiment. I calculated the gravitational constant of water. So the normal gravitational constant is 6.67 times 10 to the power of minus 11. And I say the one of water is 6.65. It's a small difference, but it is measurable. First, I didn't measure it directly, but I did a very sloppy experiment. I didn't seal it from air. There was air going back and forth all over the place, but I wear a mask. The only time I would ever wear a mask. I don't normally wear it. So I was wearing a mask. It was like in March, April, February, March, yeah, in Greece, and I would let the stick touch the buckets. I had buckets with iron and buckets with water, and I would simply compare how long it takes for it to rotate and touch the bucket. And it was messy because there was air around, so sometimes it would just drift away and not do what it should. So I did it 66 times, and I just look if iron is faster or not, because iron should be faster, have more gravity. And I got a 99.98% confidence that it's really true what the theory said, and that iron has more gravity because it has more protons and neutrons per kilogram. Because all of this negative binding energy, you can put more protons and neutrons together and you still don't have such a huge amount. You have more quarks per kilogram. So that was, I was done after 66 times. I didn't want to do it anymore. I spent like 5 hours the whole night. I gained some weight at that time actually, because if you stay up all night, you need to eat something. Anyway, so after that, I wanted to do the air-sealed experiment, the standard experiment, which is much more difficult, but actually less impressive because you don't see much happening. Instead of a huge movement over 3 minutes, you have a tiny movement where you see nothing moving at all, and the oscillation angle is only 0.0048 or something like that. It's so small. I had a computer program to measure the angles, and it was still working when my experiment was not perfect. Mm-hmm. When my experiment was not perfect, there was still a little bit air going in, and so it was not correct. And so I had too much oscillation, but then I could still use the computer program because the oscillation was not too small, so the pixels didn't get in the way. So the oscillation I got when the experiment was perfect was easy to see with the eye. You could see it with the eye, and it looked like it's as much as it should be. And actually, it took me 1 month to figure out why the hell the experiment was not working. Why the hell I was always getting gravitational constants of 10 to the power of minus 10 instead of 11. And the way I found out is it was a big factory, and the workers told me to leave because they had so many work to do, so many products to stack up, that my sister is selling organic products. It's a family business, olive oil and all this thing. So they sent me out, and I put the thing near the swimming pool, and it was horrible. There were ants crawling all over the place, and they got onto the glass, and it was like a horror movie or something. Oh my God, ants everywhere. And everything was getting dirty. And in daytime, I looked at it and was like moving a lot. And then I figured, oh my God, there's actually air going inside. And the reason was because I was using a very little tape. Maybe maybe I'm used to not use too much of everything. So I used little tape, and I even didn't fold it over to make it really air sealed. I had it just like this around this big. I had a big black container, and I didn't fold over. Then I folded over, and I used 2 or 3 tapes, and then it was right. But the difference between me and Einstein, or me and Newton, is only 2.5 seconds. So I had to look at these tiny angles for many days. I was looking at the computer, making screenshots second by second, when the whole oscillation was actually 15 minutes and 51 seconds. So you can imagine when the angle is so tiny, it's very hard to judge. Did it stop here, or in the next second, or in the next second? Is it moving right or left? I was asking my family and friends when they're walking by my computer, tell me when you think it's not going to the right anymore. So screenshot by screenshot, again, not so sure, go back again, So that's why I say the not so precise experiment before, it's to me it's more impressive because I'm more sure of it. But this one, it's just a few seconds. It's good enough to put it in my book, but I would have to repeat it with lasers, I guess. Standard way to do is you have lasers and you project it on a wall, and so you can measure very tiny differences and very precisely. You can measure it very precisely. So I have to redo the experiment, but I'm pretty sure it's right. And I'm not exactly the only one who found this, because this whole chemical gravity thing, where you have to know the chemical composition to know the gravity, I'm actually not the only one who has found this. There was a huge fuss about it actually in the 80s. In 86, Fischbach actually discovered that there's a slight difference in how things drop, like a free fall drop. Like all objects, are they dropping at the same speed? Actually, what Galileo was saying back in the days, he said all objects drop at the same rate, regardless of their mass. But the one who was writing his biography actually said the initial way he formulated the law was all objects of the same material drop at the same rate, regardless of the mass. So that's actually like he was an expert on SPD, because that's exactly what SPD is saying. Some people will say, oh, maybe he channeled it. So you can channel whatever you want. Just a joke here. Yeah, so he was right about it. And Fischbach actually discovered that there's a slight difference, very tiny difference, between the different materials dropping in a vacuum. And it was exactly according to the baryon number. Like I say quarks, he says baryon number. I just want to be more general, because you could have mesons, which consist of a quark and an antiquark, something like that. they also have gravity, so I have to be more general and say quarks instead of baryons. But the equations Fischbach wrote down, they were pretty close, but he got everything pretty messed up by not having a theory that predicts it. He observed it and wrote down some equations, but they were overly complicated because he didn't know gravity is a side effect of the strong force. So he said something very not straightforward. He said that there's a fifth force which is coupled with a strong force, and that's what we observe here, like some extra force, fifth force, and it has a certain range which was arbitrarily chosen. It was so complicated. If you see his paper, it's a huge mess. And then later people proved, or maybe even before that, I think it was about that time, 86, people proved that there cannot be a fifth force. And so then everyone just dropped it. And now there may be a few people who know about this thing, that gravity might be related to the strong force and this stuff, but it's really like almost nobody knows about it.
Very interesting indeed. Last but not least, can you define consciousness?
Yes, so according to my book has 6 chapters, and chapter 5 is about consciousness. Actually, it's a favorite chapter of a lot of people, chapter 5.1. And I'm basically saying that consciousness is, you see, when I talk, there's identity theory, and it says every brain state corresponds to one state of consciousness. But this cannot be quite true, because when I say a sentence, I have to finish the sentence for the meaning to emerge. So I say a lot of words, but in every moment, in every snapshot of me talking, it's just one sound, like so it doesn't have any meaning. And if you record my brain patterns, is just neurons firing around, and one snapshot doesn't tell you anything. And you really need a continuous thing. And that means the past must still be there somehow, in some way. Is it in a space-time way? Or is it rather, in philosophy, you have this, or spiritualism, you have this Akashic records, which say that everything we experience is still there. But Akashic records is not so clear about if it's just the past, also the future. After all, it's not a scientific theory, and it's many thousands of years old. So part of Hinduism also, I guess, something like that. I'm not an expert on these, but what parapsychologists have is the non-local realm, and that is actually also not so clear about if there's only the past, also the future. Some people try to remote view the future, but it's not really possible. I think you can only remote view the past, but even that is controversial, of course. But what is not controversial is that we are able to think, and that we are able to connect the sentence. And so in order to me saying a sentence, producing a consciousness of that sentence, it requires that there's a record of me saying that sentence. And a lot of philosophers and some physicists have also thought about what's the origin of qualia. Why are some things red and other things are blue? And in physics, it's just a frequency. Why are there colors? They don't exist in physics. Why are there colors? So my theory on colors is that red has this redness, this feeling of this hot color, because this frequency is always appearing together with hot things, glowing things, the sun, fire. And blue, it's a cold color, and it tends to appear together with the ocean. Water is typically cold. If it's too hot, it evaporates away. And the sky is blue, and we associate it with wind, so that's a cold color. And so this non-local realm, I'm different from the parapsychologist. I'm making it very clear that it only includes things that are already measured. So you cannot remote view something that is not measured yet. So Dean Radin, who is a very famous parapsychologist, he asked people to remote view through which slit of a double slit the photons go. And it has a little effect on the interference pattern, but it's actually non-local perturbance, like psychokinesis, a small effect of it. And it's not remote viewing. I think they mix up things, and I make it very clear that only things somebody experienced are part of this non-local realm. And so basically you also have the Platonic realm. Platonism believes that Platon believed that mathematics is not invented, it's discovered, and it all has this eternal existence in Platonic realm. And Penrose, who won Nobel Prize last year, he says that when we think about mathematics and logic, we have this connection to the Platonic realm, and it's like the internet, it exists in every place. And I don't like calling it a field. I also don't like to call this non-local realm a field, non-local field, because fields have strength and field strength, and it's computational. And this is not computational. The way we understand mathematics is not computational. And the only reason why this is even possible for our brains to exceed computation is because our brain is in a superposition. And we can actually prove that big things are in superposition. There are these experiments Dean Radin does a lot, where you look at a random number generator and you have ones and zeros, and you try to have it make more ones than zeros, and you basically have a 51% chance, which doesn't sound impressive at all, but over the range of 70 years, it adds up to a lot, and you get the chance for this to be coincidence is 1 to 10 to the power of 12. And if you go do a meta-analysis, it's 1 in 10 to the power of 15. So this is not a coincidence. And the interesting thing is to not ask the observer to observe the random number generator directly, but to store the results in a computer and then do something very amazing and interesting. You store it in the computer, you wait 1 or 2 days or even longer, and then you show it to the observer and look if this non-local perturbance, this psychokinesis effect, micropsychokinesis, is still working, and it still works. And for me, it proves that entering data into the computer doesn't collapse the wave function. It doesn't collapse the wave function. Yes, you lose quantum coherence. You don't have interference anymore, because big things, they're too big to have interference. The wavelengths are too small. That's why you cannot have interference with people. If I go through one door, I won't stumble just because the other door is open. So even if Hawking is right and we have this omnium state with where all universes are messed up, and I sit in this chair at the same time in that chair, there won't be interference. And many physicists, they say, oh, okay, that means the wave function collapsed, or it's the same like wave function collapsed. But it's not the same when you look at this very particular instance where the observer tries to have a slight influence on the result. Then you find you have a method of actually checking if the wave function collapsed or not. Because if it already collapsed, then you had no way of influencing anything, because it's already decided. I also invented other ways of checking when the wave function collapsed. I published a paper in 2018, which is checking for how long you can use a quantum eraser. Quantum eraser experiment is, I won't explain all of it here, you can look it up online. But basically, the amazing thing is that you can use the quantum eraser even after the photon hit the screen, which is amazing, because you would think the screen is something macroscopic and you cannot change the past about something macroscopic, but it's possible. And then the interesting thing is, how long can I delay the quantum eraser till it's not possible anymore? And so that would tell you when the wave function collapses, and I predict it's 0.325 seconds, which is the time it needs to reach the subconscious level. 0.5 seconds would be the conscious level. So, and then you can put an animal there and check, does it change this maximal delay time? In order to do the experiment, you have to freeze photons in mid-air by letting them pass through a sodium-2 gas. You can have a gas chamber, sodium-2, you make it longer, shorter, and then you can change the delay time till it hits the detector, because photons are so fast that usually it's just an instance. Any delay you have, it's very tiny normally. And that's an experiment I want to do. Dean Ray also has expressed some interest in conducting the experiment, but he says it's a bit too expensive for the budget of his lab.
Is there anything else you want to say, or come to a close?
Yeah, I have many technological applications, but they're a bit speculative. You know, for example, anti-gravity or something like that. It would be totally impossible if gravity was based on gravitons, because they're just too tiny and you cannot stop them or block them. For gluons, it's similar, but for gluons, I still have a little hope, because they're like as big as the atom core, and you could imagine to block them somehow if you had a very tiny grid, very dense. Like, you would have to have the density of a neutron star basically, but if you have only one slice, maybe there's a way this is possible. It's science fiction, but I would prefer to do this kind of science fiction than the one we have today with warp drive and all these things, which I believe are totally impossible, and most people also agree that they're totally impossible. I want to have some new type of science fiction. One thing that I haven't mentioned is that I believe that we are alone in the universe, which is very unusual, and this is probably the most unpopular part of my theory. It's basically connected to something that Eugen Wigner was pondering about. He made actually a lecture about it in German, although he's no German and his German is awful, but he made this 40 minutes, 1 hour lecture, and somehow he got through it with German, totally, all of it was in German. And he's one of the founders of this interpretation that constants collapse the wave function for Neumann and Wigner, Eugen Wigner. But he later changed his mind, and he told the reason is that he didn't know how to do this in a space-time. You have like, I measure you how you were in the past, because the light reaching me, it takes time, and you measuring me in the past. So I only collapsed your wave function in the past, so you don't even exist in the present. You're a ghost. And then you can read this in many books about quantum mechanics. Many, when they criticize the Copenhagen interpretation or the von Eugen Wigner interpretation, this order, they always say there could be an issue with solipsism, because if I need to measure everything for it to become real, then maybe only I can be real, because there's a time delay. So he gave up on it basically. But I say, if you have entanglement, you have the problem solved, because everything on Earth is entangled. You only need two particles to bump on each other, and then coherence. Then basically they get entangled. They just need to collide with each other, then they're entangled. And this entanglement needs to happen after the emergence of life, and then it counts basically, because that's how the universe is real. But this entanglement doesn't reach far out into the cosmos. It's just, we would have to bring life somewhere else in order to have life. So I could write a science fiction story, but it would be humans use atomic bombs to go close to the speed of light, reach another planet, settle down, some of them, and put plants there, plant life, then move on, come back, and because of time dilation, thousands of years pass on the planet, and then you have aliens. But I believe that they don't emerge by themselves. And I have evidence to show that we are alone in the universe, because the cosmic microwave background has, at first they discovered the so-called axis of evil. There's a funny name for a north-south symmetry in the cosmic microwave background. It's a bit hotter in a certain direction. And if you check Wikipedia, it tells you that the Milky Way has a certain speed, and you wonder, how did they measure the speed? Basically, they assume that this temperature difference is just a redshift. So it's a local movement of the Milky Way, they think. And that's fine, sort of, but then you dig deeper and you find it doesn't work. The first problem you made is there are other cold spots. There are actually four major cold spots in the cosmic microwave background. And in standard theory, for inflation theory, for example, you cannot have any fluctuations that are more than 2 degrees in the night sky. So everything bigger would have to have there shouldn't be connections over the night sky over large distance, because there was no communication. Would have to be higher than light speed for them to level out. And so you could have my tiny fluctuations, but they should not be connected. The cold and the hot spot should not be together. But so you have, and the position of those cold spots are very particular. They're in the north and south pole of Earth, and the north and south pole of the plane that's defined by the Earth moving around the sun. So then you can look how precisely are the north and south pole of Earth aligned with those cold spots, and then you can calculate what's the chance against odds. What's the likelihood for it to be a coincidence? Because Wikipedia says maybe it's a coincidence. Like you ask Professor so-and-so say, oh, maybe it's a coincidence. So the chance is 1 in 3,500. And Penrose is the only other person aside from me, I think, maybe, who is actually caring a lot about these anisotropies, about these non-Copernican structures. But all he tries to explain is the existence of these large cold spots. He tries to explain them with black holes from a former universe. That's his cyclic cosmic, the CCC model. But it cannot explain the position of the cold spots. So he calculated a chance against odds of 1 to 3,000. They really printed out simulated cosmic microwave backgrounds, CMBs. And yeah, but if you really look at the position, then you get 1 in 3,500. And there was an Indian physicist, cosmologist actually, or astronomer. He looked at other sources of radiation, quasars, powerful galaxies driven by a large black hole. And he thought, let's look at anisotropies there. Is there some alignment in the sky like this? And he found a different direction and a different speed totally. So you cannot explain away these anomalies using a local movement into a certain direction. It just doesn't work at all. So this is the evidence that all the wave functions in the universe collapse here on Earth. It could be a coincidence, but maybe not. And I think it's not. Before, I thought there's even more evidence, because I looked at that the galaxies around us are arranged in concentric shells, 7 of them. And for a long time, I thought, oh, maybe that's also because of wave functions collapsing here. But that's actually explained with acoustic shock waves in the early universe can be explained. And I did calculations in my theory, and it explains it quite well.
Very nice.
And one last thing. The reason why it's hotter and colder in the CMB here, and that sounds very crazy, but basically I'm saying because most observers are more close to the equator, so the CMB is a tiny bit hotter there, and these differences are not so big, just 100,000ths of a degree. And so I sometimes call it cosmokinesis. Like it's night and you try to see a little tiny bit more, you have prey and you hunt prey, and then there's a slight tendency for more photons to reach where there's an observer. So you have observers here, and a tiny, really very tiny, it's a 10,000th of a degree. The effect is very small, but I did many calculations on this, also looking at the effect size, and it's pretty plausible that this can be a very tiny settle effect over millions and millions of years, because the universe is built from the present into the past. Even now, at this moment, you collapse the wave function of the early universe near the Big Bang, and I say that we see only 1% of the universe. Like the other people, they think, oh, we should be seeing the first stars, and they're so disappointed that we don't see the first stars because they still have heavy elements. I say the universe is so old that we only see 1% of it between us and the cosmic microwave background. Yes.
Okay. Disclaimer.
Mm-hmm.
The fact that I helped you through this interview, through this conversation, to express your opinions, ideas, viewpoints about the fundamental nature of reality does not mean that I accept them. It does not mean that I consider your theory SPD valid or true. In any case, it was an honor and pleasure to be here with you. Thank you, Sky.
You're welcome. Nice to talk to you. See you. Bye.
Stop recording.